In section 3.6, this section is going to kind of serve as a mid-chapter summary of the things we've kind of looked at so far, specifically the ideas and concepts we studied in 3.3, 3.4, and 3.5, so that we can get a good analysis of graphs and how they behave. So this slide's going to serve as all the guidelines that we need to know when we're trying to analyze graphs. So the first thing you see is something you've known for a long time now since algebra, is that to find x-intercepts, we set our equation equal to 0 and solve for x. The reason we do that is because we know the y value at an x-intercept is 0. To find y-intercepts, it's kind of the reverse. We set x equal to 0 and solve for y, because we know at a y-intercept, our x value is 0. Vertical asymptotes, we saw this prior in this class, so it's just there as a little reminder so we can have it there as a reference. In the last section, we studied horizontal asymptotes, so I'm going to go ahead and put that there as well, just so you can have that for an additional reference. What did we study in 3.3 and 3.4? Well, we studied how the graph of a function behaves. The first thing we kind of looked at was finding critical points using the first derivative, which meant we needed to set the derivative equal to 0, and if possible, find where the derivative is undefined. Then, to use those critical points, we would put them on a sign chart so we could find where a function is increasing or decreasing. And then within that, we could determine if we had any relative maxes or mins, depending on the derivative changing signs. In 3.4, we looked at inflection points using the second derivative. So to find those candidates, and that's the key, they're candidates, we would set the second derivative equal to 0, and if possible again, find where the second derivative is undefined. To determine if those points were indeed inflection points, we would set up a sign chart so that we could find our intervals of concave up and concave down. And then if we saw a change in the second derivative sign, we knew we had an inflection point. So this slide again will kind of just serve as an overview and a quick reference for what we learned in 3.3, 3.4, and 3.5. Okay, so let's attempt to run through a complete analysis of this function, x to the fourth minus 10x cubed plus 5. The very first thing I'm going to observe right away is, since we don't have a rational function, a function that is a fraction, there are not going to be any asymptotes for this particular function, so we can kind of get that out of the way real quick. The other thing I'm going to do real quick, because we had this ability before calculus, is to get the x and y-intercepts out of the way. Y-intercepts happen when we plug in 0 for x. So f of 0 is 5. So we have one y-intercept at 5. To find the x-intercepts, we need to set our equation equal to 0, because at an x-intercept, our y value is 0. Here we can't solve this by hand. You'd have to use your TI-89 to solve it for you. So I'm going to go ahead and put up those two x-intercepts, one at 0.8 and one at x equals 10. Okay, now let's jump into what we did in 3.3 and 3.4. First thing we're going to do is find the derivative of our function so we can get some critical points. When we take the derivative and set it equal to 0, we can factor that expression. Once it's factored, we can set those two factors equal to 0, and we'll find that we get two critical points, 0 and 7.5. To understand what those critical points are, they might be relative maxes or mins, we need to make a sign chart. So here's our sign chart, and again we're labeling it as f prime of x. So we know that it's not our second derivative sign chart. Okay, so let's pick a number to the left, in the middle, and to the right. I'm going to let x equal -1. If you plug -1 into your first derivative, remember this is our first derivative sign chart, we'll get -34. But I really care that I got a negative sign. In between 0 and 7.5, I'll pick 1, and when you plug that into the first derivative, you'll get -26. If you plug in a number to the right of 7.5, I'll pick 10. You'll get 1,000, but really all I care about is that that is positive. So you'll notice our graph is decreasing, decreasing, and then increasing. So did we end up with any relative extrema? Well, yes. At 7.5, our derivative went from negative to positive, which means we have a relative min at 7.5. I want to find, since we're trying to kind of figure out where these points are on the graph, I'm going to find the point at 7.5, or the y value at 7.5. F of 7.5, and that's not a typo, it's a really big y value in the negative direction, is negative 1049.7. So we could plot that point so we knew exactly where it was. But the most important thing is that is a relative min. Okay, next we can go on to our second derivative analysis from 3.4 and find some candidates for being points of inflection, which means we need a second derivative. When we take that second derivative and set it equal to 0 and factor, we'll get two candidates for points of inflection, 0 and 5. So again, those are just our candidates. We don't know if they're actually points of inflection until we go to our sign chart. So we're going to set up our sign chart, but now again we're going to have to label this sign chart appropriately. That is our second derivative sign chart here. So we're going to pick a number to the left, in the middle, and to the right. And when we pick those numbers, you've got to be careful. There's a lot of stuff going on in this big problem. We're taking those values and plugging them into the second derivative. If we pick x to be negative 1 to the left of 0, we'll get 72, which is positive. I'm going to pick 1 in between 0 and 5. When I plug it into the second derivative, we'll get negative 48. Only care that it's negative. And to the right of 5, I'm going to pick 10 as my x value, and when you plug that into the second derivative, you'll get 600, but the main thing here is that it's positive. Since this is our second derivative sign chart, we don't want to put arrows going up and down. We want to draw concave pictures. If our second derivative is positive, our graph is concave up, and if our second derivative is negative, our graph is concave down. So now we can get back to the question of, did we have inflection points at 0 and at 5? Well, now we know the answer to that. We do have an inflection point at 0 because the sign of the second derivative changed. Since I want to know that point, I'm going to figure that out by plugging that into the original function. F of 0 is 5, so we can plot that inflection point. We also discovered that at 5 we have an inflection point. And since I want to plot that point on a graph, which you'll see in a moment, I'm going to find the y value by plugging that back into the original equation. F of 5 is negative 620. Okay, we did a lot of analysis and things to kind of understand what this graph might look like. So now let's go ahead and do that. Let's take a look at what this graph looks like. So I've plotted 3 points that you can see here. I've plotted my y-intercept, which, by the way, I didn't point out, also is our inflection point. You'll notice our inflection point is the same as our y-intercept, but that's just a little coincidence, I guess. We have another point we can graph, 5, negative 620, which is another inflection point, and then we found our relative min is 7.5, comma, negative 1049.7. So let's go ahead and take a look at each of the regions of this graph. To the left of 0, we know our graph was decreasing if you look at the sign chart for the first derivative. But if you look at the sign chart for the second derivative, that was supposed to be concave up, which you can see clearly right there. Between 0 and 5, based on our sign chart, that piece of the graph was supposed to be decreasing. And it is. And then you'll notice it was supposed to be concave down, which, again, that piece is. From 5 to 7.5, our graph is still supposed to be decreasing based on the sign chart, but now it changed over to concave up, which meant we had our 2 inflection points. And then to the right of 7.5, our graph is supposed to be increasing, and it's still concave up. So the main thing I want you to take away from this whole analysis is that we're really not trying to graph these functions by hand. What we're trying to do is just analyze them, and the reason I have the graph here is just to verify that our first derivative sign chart and our second derivative sign chart makes sense based on this picture. Okay, I'm going to do one more example since these examples are pretty long and involved, but this time I'm going to do it with a fraction, a rational expression. So, just like the last example, I'm going to go after some of the easy things first. The y-intercepts, that's when we plug in 0 into our function, which in this case we get 2/3 for a y-intercept. To find our x-intercepts, we set our equation equal to 0 because y has to be equal to 0. When we solve that little equation there, we'll get x equals 2. So we have our y-intercept, we have our x-intercept. The next thing I'm going to jump to are our asymptotes. Since our function is a fraction, and it's a simplified fraction, there's nothing we can do to simplify it anymore. We know a vertical asymptote will occur when the denominator is equal to 0. And that's nice and simple, so we have a vertical asymptote at x equals 3. Horizontal asymptotes, what we covered in the last section, 3.5. That concept involved us knowing that we need to take the limit of our function to infinity. Here, this is a nice simple one to solve if you remember the steps. What we need to do is consider the highest power in the top and the bottom, simplify that expression, and then take the limit. The limit of 1 of a constant is just a constant. If we get a number as our answer, we know we have a horizontal asymptote at that number. So our horizontal asymptote is at y equals 1. Okay, so now we can get back into our first derivative and second derivative analysis. We need to find the derivative to find some critical points. And since we have a fraction, a function over a function, we need to use the quotient rule. So again, if you need to go over the steps of the quotient rule, pause the video, make sure you're okay with that. But once we simplify our first derivative, we'll get -1 over x minus 3 squared. And we're going to have to set that equal to 0. And you'll notice, when we set this equal to 0, we shouldn't get any x values. You'll notice, if you were to cross multiply this way, we would end up with 0 equals -1, which we know can't be possible. So we don't get any x values for when the derivative is equal to 0, but you have to keep in mind of the other case. The other case is when the derivative is undefined. And when is our derivative undefined? Well, that's when the bottom is equal to 0. When is the bottom equal to 0? Well, that's easy to see. That's at x equals 3. But you gotta be careful. You might automatically think, oh, we got an x value, we have a critical point, and then kind of go from there. But if you're thinking carefully about this, you'll notice from before, we had a vertical asymptote at x equals 3. So we know that really can't be a true critical point in the sense that it's a relative max or a relative min. But we still want to put that on the sign chart so that we can figure out where this function is increasing or decreasing. The thing I'm going to do, just to make sure we don't forget that it can't be a max or a min, is I'm going to label that as a vertical asymptote. Now, I'm going to do something a little bit tricky here, and I don't mean to confuse any of you. If you want to ignore what I'm doing right here, that's okay. If you want to just pick a number to the left, plug it into the derivative and see what you get. Pick a number to the right, plug it into the derivative, see what you get. That's perfectly fine. But I'm going to notice something about my first derivative, and it's this. You'll notice the top of this first derivative will always be negative. It's a -1. The bottom of this derivative, it doesn't matter what number you pick for x, you're going to subtract 3, but ultimately you'll square that quantity, which will always make it positive. So we can observe that our first derivative will always be negative. So if it's always negative, then we can label it, or we can label our sign chart with just negatives. But like I said, I hope I didn't confuse anybody by doing it this different way. I just observed that we didn't really have to pick a number to the left and to the right. I think for most of us, though, that would probably be the easiest way to do the vast majority of problems, because this little trick might not always work. So our function is decreasing before 3, and it's still decreasing after 3. Okay, on to our second derivative analysis. And to take the second derivative, I'm not going to take the derivative of this version of the first derivative. It's better to rewrite that as -1 and then take that stuff from the bottom to the top as a -2 power. I guess you could use the quotient rule if you really wanted to on that, but it'd probably be easier in some sense to just take that x minus 3 squared to the top as a -2 power. When you do that, you'll get that second derivative. And since we need to set it equal to 0, I'm going to send that -3 power down to the bottom. So this is kind of just the culmination of all these skills we've been practicing throughout this chapter. So hopefully you're good with those skills and not getting too lost in these steps. Okay, let's solve this simple little equation here, or hopefully simple at this point in this class. If we kind of cross multiply those, if that helps you see it, we'll get 0 equals 2, which cannot be. So we don't get any x values from that. But we need to remember, we also need to check when our second derivative is undefined. It's undefined when the bottom is equal to 0, and that of course happens when x is equal to 3. But just like with our first derivative, we can realize something. Since x equals 3 is our vertical asymptote, there's no way that that's going to be a point of inflection. But nevertheless, we'll still continue on with our second derivative sign chart because we still want to know where this graph is concave up and concave down. I'm just going to label that 3 again as VA so we don't mistakenly call it a point of inflection. Okay, so in this one I can't do the little trick where I don't have to pick a number to the left and to the right, so I'm going to just go back to that regular way of doing the sign chart. I'm going to pick 0 to the left and plug it into the second derivative. You'll get a negative fraction, so we'll label that as a negative. To the right of 3, I'm going to plug in 4 into the second derivative. If you plug in 4 into the second derivative, you'll get a positive 2, and then we'll see we have concave down to the left of 3 and concave up to the right of 3. But had we not noticed that 3 was a vertical asymptote, you might have called 3 a point of inflection. So be careful. That vertical asymptote is there, so x equals 3 is not a point of inflection. Continuing with this problem, now we're going to focus on the graph since that didn't fit on the last slide. So let's take a look at some of the features of the analysis of this function to see if we can get a good looking graph for it. So the first thing I'm going to graph are vertical and horizontal asymptotes. The only other piece of information we have point-wise that we can graph are our intercepts. We have an x-intercept at 2, 0, and we have a y-intercept at 0, 2/3. So I'm going to graph those 2 points. So we really have just 2 regions to this graph, to the left of 3 and to the right of 3. So let's take a look to the left of 3 to see if we can get a good looking graph. With those points already plotted, we know our graph has to go to those 2 points. So our graph has to be decreasing, but concave down. So the part of this concave down picture that we need to be drawing is this piece right here that I'm drawing over. That's the piece of concave down that's decreasing. We don't care about the other side because that's increasing. So we want to draw a picture that's concave down but decreasing. So something like that. To the right of 3, we have a graph that's supposed to be concave up and still decreasing. And I'm going to again just kind of highlight it here in a manner of speaking. The part of concave up that's decreasing is this left side. So the picture we're looking to draw is the decreasing part of concave up. And the only way to make that happen so that we're following our asymptotes is to draw that concave up piece that's decreasing right there. And that's the final graph of x minus 2 over x minus 3. Okay, these last 2 slides involve examples that I think are going to be pretty challenging, especially because they involve a very conceptual use of what we've learned up until now. What we're going to be given here is a list of properties of a graph that we don't know what it looks like. And we're going to attempt to take these things and try to draw a graph. So the first thing I want to point out, just so you don't get frustrated with these, is in terms of the AP test, you really just need to understand what these mathematical things that are listed here mean. If you kind of have a hard time seeing how to translate all this into a graph, that's okay. That's not going to be asked of you on the AP test. But we definitely have to understand how to translate all of these little math things we were given into some sort of wording that we can understand. So let's jump right into it, and that's what we're going to do. I'm going to attempt to translate each of these things into something that means a little bit more to us, and not just this math notation. So what does it mean if I tell you f of 2 and f of 4 are equal to 0? Well, we know that those would be x-intercepts. If you have a function that has a value of 0, then at those x values, it has to cross the x-axis, which makes it an x-intercept. So we know there are 2 points we could plot right away, and that would be the point x equals 2 and x equals 4. Those are our x-intercepts. The next piece of information that we're given is that f of 3 is defined. Basically, that means we don't have a hole or anything like an asymptote or something like that at x equals 3. Now onto the calculus notation. What would it mean for the first derivative to be less than 0? I'm going to get to this second part in a moment after the word if, but what does it mean for the first derivative to be less than 0 or negative? Well, that means that our function is decreasing. But where is it decreasing? Well, they tell us that it's decreasing for x less than 3. If I write that in interval notation, all the values that are less than 3 would be negative infinity to 3. The next piece of information they give us is that the derivative at 3 does not exist. If the derivative does not exist, then we know there's some sort of sharp corner or vertical tangent or a cusp, if you want to word it that way, at x equals 3. The next piece of information they give us is the first derivative is greater than 0, which means it's positive. If you ever see that the first derivative is positive, you know the function is increasing. But on what interval in this case is it increasing? Well, it's telling us that x has to be bigger than 3. Well, the numbers that are bigger than 3 are 3 to infinity. The last piece of information they give us concerns the second derivative, and it says the second derivative is less than 0. If the second derivative is less than 0, it's negative. And if our second derivative is negative, we know the graph is concave down. But where is it concave down? Well, in this part, they don't give us an interval, so to speak. They just say x cannot be equal to 3, which means it's concave down everywhere except at x equals 3. So if you can handle doing all this translation of this mathematical notation, you're okay with these problems. On the AP test, you'll never be asked to graph anything like this, or at least I've never seen a question like that. But let's attempt to understand why we're going to get the graph that you're going to see below. So we at least know we can graph 2 x-intercepts. So the big question is this. At x equals 3, we have a point because it's defined. But is it going to be above the x-axis or below the x-axis? Well, if you think about it for a moment, it's going to be below the x-axis. We don't know exactly where it's going to be. I'm going to just put it somewhere down there. But we know it's below the x-axis for 2 reasons. This function is decreasing to the left of 3 and increasing to the right of 3. The only way you're going to be able to pass through the points 2 and 4 in that manner is to be below the x-axis at x equals 3. The other thing we know is that this graph is always concave down. So you can see to the right of 3, our graph is decreasing and it's concave down. To the right of 3, it's increasing, but still concave down. So not too terribly hard, but not very easy to make this graph. The main thing I hope you guys focus on is translating this mathematical information into words and something that you can understand a little bit better. That's the important skill you should take away from this slide. And one last example, like the previous slide. So let's start jumping right into this. Let's translate this first piece of information. We're given that the first derivative at 0, 2, and 4 are all equal to 0. So there's several different ways we could maybe write this information, but I'm going to choose to write it this way. We have horizontal tangents at x equals 0, 2, and 4, or that is, and I'm going to have to write this in if you need that, the slope is equal to 0 at those points. So a few different ways you can write it, but ultimately that's the information we're given. Okay, second piece of information we're given is that the first derivative is greater than 0. If the first derivative is greater than 0, it's positive. And if the first derivative is positive, we know our function will be increasing. On what intervals is it increasing? Well, the first interval is when x is less than 0. What x values are less than 0? Well, negative infinity all the way to 0. The next region they give us is from 2 to 4. And I guess that really doesn't need to be rewritten if you can see it easily in this form. And even the x less than 0, we didn't have to rewrite it in this interval notation. But I'm choosing to go ahead and do it that way. So we can write the interval from 2 to 4 as the interval notation, parentheses 2, comma, 4, close parentheses. And again, remember, this is not x comma y. It's not a point. Okay, third piece of information we're given is that the derivative is less than 0. The first derivative is less than 0, which means f of x would be decreasing. On what intervals is it decreasing? The first piece of information we're given is from 0 to 2. And again, I'm just choosing to rewrite this in a shorter kind of notation, this interval notation. But again, note, this is not the point 0, 2. This is the interval from x equals 2. I'm sorry, from x equals 0 to x equals 2. The other interval that the function's decreasing is when x is greater than 4, and we know the values that are greater than 4 go from 4 to infinity. Two more pieces of info. The second derivative is greater than 0, which we know to mean that the function is concave up. If the second derivative is positive, our function is concave up. On what interval is the function concave up? Well, from 1 to 3. One more time, I'll go ahead and say it. This is not the point 1, 3. It's the interval notation for the interval x equals 1 to x equals 3. The last piece of info we're given is that the second derivative is now less than 0 or negative, and if our second derivative is less than 0 or negative, we know the function is concave down. And on what intervals? Well, x is less than 1, so that means all the values from negative infinity up until 1. And then they tell us x is greater than 3, which means all the x values from 3 to infinity. So, unlike that last example, there's one extra piece of info I can pull out of this stuff that we've listed here. We know there's some points of inflection. How do I know there's some points of inflection? Well, you'll notice the graph is supposed to be concave down from negative infinity to 1. And then right above that, we know it's concave up from 1 to 3. And if we jump back down to the bottom, it's back concave down from 3 to infinity. So a little bit of an observation you can make. From there to there, we had a change of inflection. And from there to there, we had a change of inflection, which makes those points of inflection. So just a little bit of extra info we can pull out of this problem. Okay, this one's definitely a lot harder to graph compared to that last one. So let's just take a look at the pieces of this graph to understand why this is the graph. At x equals 0, our graph is supposed to be increasing. I'm sorry, to the left of 0, our graph is supposed to be increasing and concave down, which you can see. From 0 to 1, our graph is still concave down, but decreasing. From 1 to 2, our graph is still supposed to be decreasing, but now concave up because that was our point of inflection. From 1 to 2, again, it's decreasing and concave up. From 2 to 3, still concave up, but now increasing. And again, here's our other point of inflection, because now from 3 to 4, we're changing to concave down, but we're still increasing. And then to the right of 4, we're decreasing, but still concave down. So I went through that analysis real quick, so definitely something you should pause and kind of rewind and go over and make sure you understand why the graph looks this way. But remember, the graphing portion of these problems is not the major thing I need you to take away from it. The major thing I need you to take away from these problems is, can you do all of this? Can you analyze all that math notation and translate it into English, so to speak?